In this module, we'll be covering the chi-square. This should look pretty familiar to what we've been doing with the z-test and t-test. It's the same basic logic. Remember how we talked about the 5 steps of hypothesis testing are going to be consistent through the whole course, so those haven't changed. All that's changing is how we are calculating the test statistic. Why might you want to use the chi-square? Well, it comes down to working with data that you can't apply the same kind of numerical operations to that we've been doing with the other tests. For example, suppose we were interested in whether or not there was a gender difference in major declaration in psychology. And we go and we collect the data from the department and we find that there are 60 males declared in psychology and 90 female. Okay. So how might we compare this data? Remember what we've been doing so far is we've been calculating central tendency and a variance, like a mean and a standard deviation. But there isn't really a mean or standard deviation to be calculated here. This is what we call categorical data. Right? This isn't numerical data. We can't do operations here. Like we can't add it up and divide by the total. Right? We just have 2 categories. This would be similar to asking somebody their favorite color. Right? And if you get 3 people who like red and 4 people who like yellow, what's the average color? Right? You can't add the 3 red to the 4 yellow and divide by 7. Right? So we have to treat that kind of data fundamentally different. And that's what the chi-square method is. The chi-square statistics works with percentage data, works with categorical data, it works with any kind of nominal data, but it's the same core 5 steps of hypothesis testing. This is what the chi-square equation looks like. So what we're working with here is this x squared is the chi-square symbol. Right? And so what we do is we're taking the observed data. That's what we see in our data. In this case, the observed data is the 60 male and 90 female. And we're taking that observed data, and what we do is we subtract what we would expect from that data if the null hypothesis was true. So if we come back to here and we ask ourselves, what is the null hypothesis? Now, the null hypothesis would say that there is no difference in the number of male versus females declared for psychology, right? That these numbers should be exactly the same. Right? So the expected value, if the null hypothesis is true, is that these would be equal. So if we look at this, there's 150 people total then, right? 60 plus 90 is 150. So if there was no difference between male and female, the expected value would be 75 male, 75 female, right? They would be equal. So what we're doing is we're testing the difference between what we observed and what we would expect if the null hypothesis is true. And if our observed data is statistically significantly different from what we would expect if the null hypothesis is true, then we can reject the null hypothesis. So what we're doing is we're taking the observed data, minusing the expected, and then we square it. That gets rid of any positive or negative issues, so we get a magnitude value, and then we normalize it to the expected value. So it's observed minus expected squared divided by the expected. We would do this for each category that we're testing, so then we have to sum them up. So the summation sign simply refers to if we had more than one category we were testing, we would sum up those values. We then get a final chi-square value, and we are going to compare it against the chi-square distribution. It looks very different than what the z-test or t-test distributions would look like because we are squaring it. We never have a negative value, right? And it's going to depend on our degrees of freedom. The degrees of freedom is calculated by the number of categories, right? So minus 1. So it's the number of categories minus 1. So in our case, we had the category of male, the category of female. That's 2 categories. So the degrees of freedom would be 1. Just like with the t-test or the z-test, we have to take our calculated degrees of freedom and find a cutoff value. So you can see in table 13.2, our degrees of freedom is 1. And so if we use a significance threshold of an alpha 0.05, our cutoff is going to be 3.841. Right? So this should be a fairly straightforward calculation. Right? The complexity with the chi-square is in determining the expected value. That's the hardest part of it, right? Is we just take observed minus expected squared divided by expected. We do that and then we add them all up, right? So figuring out what the expected value is usually where the conundrum is going to be. So, right, we have to add up all of the categories and split them evenly, right? If the null hypothesis is that there is no effect. Okay, so the complexity here is almost always going to be in finding the right expected value. So let's hop over to Google Sheets and we'll take a look and see how we can solve this. Okay, so here we are, and over here in Google Sheets we have the same exact data. We have our psychology declared majors, male, 60, female, 90, right? So these are going to be our observed values. Right? So let's add a column just to make it obvious that we have our observed values. So let's think about our expected values. Remember, expected values are going to be equal to whatever our total number of observations were. In this case, the null hypothesis says that there is no difference, so we have 150 people total, which means that our expected values are going to be 75 and 75 equal, right? So now we have to do our calculations. So let's do the first chi-square for the male data. And so what we do is we take the observed data, which is 60, minus the expected, and then we square it. And then we take the results of that and we divide it by the expected value. Okay. So that's the chi-square for the male. So let's look at the female chi-square. So we take the observed, in this case is 90, minus the expected. Then we square that. Right. And then we're going to take that divided by the expected, right? Since the observed in both categories is the same distance from the expected value, they're going to be the same. And remember, the last step is to take the chi-square from both categories, right? And we are going to sum all of that up. We're going to add them all together. That 6 is greater than the 3.8. That was our cutoff. And so we can say that based on the chi-square test, we can reject the null hypothesis. That's chi-square. Chi-square can also be used to deal with percentile data. But we can't use the raw percentages as part of the calculation. You always got to convert back to the actual number. So you can't use, like, say, 30% as your chi-square value. Instead, you have to figure out the number of people that are represented by that 30%. So this is something that I was looking at earlier today, which is a yearly survey that occurs after elections. The main ones are the presidential elections, where they look at the degree of trust in the electoral system. And that's a big topic right now. And what this did is this looks at about 2,000 people, and it asks them along party lines, do you trust the electoral system? And what they are finding, of course, now, not unexpected, is that there's a big difference between what the Republicans and the Democrats feel in terms of their expectations for the accuracy of the election, with Democrats saying 90% trust it, Republicans 26%. However, I found interesting that we go back to 2016 and we see that it was 73% of Republicans said they trusted it, while 39% of Democrats said that they did not trust it. And in fact, if you follow back every presidential election for how long they've been doing this survey, you find that whatever party wins trusts the election, whichever party loses doesn't. But let's take a look at this and let's even ask, well, has there really been a significant shift? Is it really true that there has been a shift from 2016 in terms of what the Republicans and Democrats feel about the trust of the election? And since we're dealing with percentages, right, remember the first step we have to do here, right, is we're going to have to convert this into actual counts. So 2,000 people were talked to total. So it was actually, what it was 1,000 Republicans and 1,000 Democrats were asked about this. So we're going to have to convert our percentages into counts. So we take our 26% of Republicans and we times it by the total that were asked. So 260 trusted the elections. Now we take our 90% of Democrats, times that by the 1,000 Democrats that were asked, we find that 900 trusted it. Same thing occurs for the 2016 data, where we find, right, that we take our percent, multiply it by n, right, and then we're going to take our percent and multiply it by the n. So now we have our data for 2020 and 2016. Now we can apply the chi-square test. Right? So let's look at the chi-square test. We'll do the Republican chi-square test first. Remember, in this case, my hypothesis says that there is a difference between the 2020 results of the survey versus the 2016 results of the survey. Right? So the null hypothesis is that there is no difference. So what's the expected value for the 2020 data? If there's no difference between the 2020 data and the 2016 data, the expected value, or the null hypothesis value, should be the 2016 data. Right? So in this case, I'm not adding them together and finding the 50% mark. Instead, what I do is I take my observed data of 260 Republicans, and I minus the expected outcome if the null hypothesis was true that there was no difference of 730 people. We then square that data, right? And now we're going to take that result and we are going to divide it by my expected data of 730. I'll do the Democrat chi-square. We'll do 900 is the observed minus the expected, which should be 390. I must have messed up on my math here. Sorry about that. Sorry about that. There we go. I'm at 390, and then we square that. Right? And now we take the results of that. We divide by the expected, it's 390, and then we now sum these up, and you're going to find a ginormous chi-square. Not unexpected. There was obviously a huge difference here. But I'm just showing you how to work with percentages, and it's always kind of fun to work with actual data, and that's how you work with the percentages. So hopefully the chi-square seems pretty straightforward. It's the same 5 hypothesis steps that we've done. We're just working with categorical, nominal, percentage data. The key is always work with counts, don't work with percents, and pay attention to what your expected value would be. Remember, your expected value is always what it would be if the null hypothesis was true.